So this formula, if you look at it carefully, this formula should look really similar to the arc length formula. That's because it's really just looking at an arc length in a couple of different places or in a couple of different directions. So the idea behind this is to take a look at your surface and look at the domain that your surface is in. And to break this up into little rectangles like you did before. And then if you focus on one little rectangle and then you see the projection up there, you're going to get something that is not quite a plane, but it's really close to being a plane. And so what you could do is you can figure out, maybe I should change colors there. You can figure out the surface area here by looking at the area of the plane. Well, the area of the plane is really just a parallelogram, doesn't it? If it's small enough, it just looks like a parallelogram. So what we could do is we could take a look at a couple of vectors back in 2 dimensions down here. Let me draw my arrows correctly. Back in 2 dimensions, I have these arrows. They actually have length, the delta x and delta y, right? And then when we bring that up here, we get these tangent vectors that look like they're pretty close to it. So we really, if we use this tangent plane approximation, that would approximate a little piece of the area of the surface that we're looking at, then we can just add up a whole bunch of them, and then we would get our actual area. So how do we do that? I think the idea is projecting it up and getting those tangent vectors. Do you remember what happened when we projected a tangent vector? Or do you remember how to get those tangent vectors here? I think it was something like, I don't know. One of them was like, what was it? I forgot. This is going along the y, and x is fixed. So x is fixed, go along the y, and derivative with respect to y. Remember that vector? Probably in your notes. I'll tell you where it is in your notes. It was on October 1st in your notes. Remember that? Of course not. So now I'm reminding you, and there's where it is. So where did the one come from? That's later, after we cross the product, after we do the cross product. So yeah, so these are the tangent vectors that we're looking at. Let's go back to today. This is today. And so we got this one for one of them, and then the other one, 1, 0, fy of x, or fx. And then, you know, it's some delta x, delta y business that gives the length of these things. It tells you how we're scaling it. Delta x, delta y. And then when you take the cross product of them, and you'll eventually get this thing over here. Oh wait, it's a cross product. So this is two vectors. And do you remember how to find the area spanned by two vectors? The parallelogram, area of the parallelogram spanned by two vectors. That's what I was trying to say. Do you remember how to find that? Something with a cross product. Yeah. So it's the magnitude of the cross product. And if you're looking for a triangle, it's 1/2 times that. I think that was in your test, in your first test. Yeah. Okay, so area of parallelogram, I'm abbreviating. This is parallelogram, is equal to the magnitude of the cross product. Ran out of room there. And so, well, when you take the cross product, you're going to get that fx, fy minus 1. And then we have a couple of scalars here, delta x, delta y, which is just delta x, delta y. And then when you take the magnitude of that, these delta x, delta y just go outside. And then you take the magnitude of this. And what's the magnitude of this? And delta x, delta y are positive scalars that can just go outside of the magnitude sign. So that's it. Say it again. Yeah. They're all equal to each other. So the area of the parallelogram, oops, there's my parallelogram, is equal to this. And then we add up a whole bunch of parallelograms. I think I have an animation of that, and maybe I'll look it up while you guys are taking your quiz. You guys still have a quiz today. Okay, so let's see if we could do a quick example. So this is how the formula is derived. And I think this piece of information, I don't care about the example I'm about to do, but what's important here is to try to see where the derivation of the formula came from. And it's similar to the arc length formula, but you know, it's for a two-dimensional version. And later on, we're going to talk about surface areas or surface integrals in chapter 16. And so this would be, you know, a good background thing to look at. All right, so let us do an example. If we can do an example in 3 minutes, maybe number 3 or 4. Let's do number 4. So we have a surface and lies above the triangle with vertices 0, 1. So I think what we need to do first is to try to figure out what this region is. So let's figure out the region. We can graph it. We got 0, 0, 0, 1, and 2, 1. 1, 2, 1. That's up here. Okay. So we can decide now or later what we're going to integrate with respect to first. And I think because this is a, I guess we could do either way. If we integrate with respect to y first, we would go from a line to a y is equal to 1. But if we integrate with respect to x first, we're going to go in at 0, which might be an advantage. I think either way would be just as easy probably, but I'm going to take advantage of the fact that if I integrate with respect to x first, drawing a line parallel to the x-axis, my lower limit is going to be 0, and that could be helpful. So with respect to x, I'm going to go from 0 to, now I need to figure out what this function is. It looks like I have a slope of 1/2 or 2. I think it's 1/2, right? So y, yeah, it's 1/2. So y is equal to 1/2 x, and the y-intercept is 0. So that's that. And if I solve for x, because I'm using x limits first, x is going to equal to 2y. So that's my upper and lower limit for x. And I'm going to integrate on the outside integral from 0 to constant 1. Remember, your outer limits have to be constants. All right, so that's the region part. Now I need to figure out my integrand, which is just a couple of derivatives. Fx is going to be 3. Fy is going to be 4y. And then that's it. So I'm going to go ahead and write my double integral. And I'm going to say that my integrand is going to be fx. So that's 3 squared plus 4y squared plus 1. And then I'm going to integrate with respect to x first, I said. X goes from 0 to 2y. And then I'll integrate with respect to y from 0 to 1. And so I think I did x first because if I do x first, I'm going to go in here into the region, and my lower limit's going to be 0. If I would have done y first, I would have gone in here and I would have a non-zero, which is probably going to be not bad at all. It's not going to be that much harder. Although now that I'm looking at this integral, if I integrate this integrand with respect to y first, I would probably have to do trig substitution. Whereas if I integrate this with respect to x first, then it's just going to be an x. Right? So it'll be easier that way. And then if I put in the limits 2y, then my second integral is probably going to be just a simple u substitution. Okay? So I'm not going to finish this. Maybe I'll finish this while you guys are doing the quiz, but I'm going to give you guys a quiz now, and then we come back, we'll continue on our triple integral. All right, pass it up, please. You guys don't have to individually come up. So I decided to do the integral here. with respect to x, is x times this, because this thing is only constant. And then evaluating from 0 to 2y is 0 to y, so it's just 3y. And then now you can do these substitutions. Easy to do. I even checked it. Well, Wolfram Alpha gave a weird answer, but I checked that answer, and it looks like it's the same. Sure. Okay. All right, so let's go back to triple integrals. And last time we were talking about volume, so let's do a volume problem. This is an interesting problem in the sense that when you're doing these integrals, there's a bunch of different ways to do them. So it turns out that when you do a triple integral, there's actually, if your solid that you're looking at is if your solid is of the right shape, then you could do this in 3 possible ways, although they say 6. Oh, I guess 6 possible ways. Yeah, with a double integral, you can only do it. There's 2 possible ways to do it. You could do it with respect to x or with respect to y. But when you have 3 variables, triple integrals, then you can do it as x, y, z, or x, z, y, or z, x, whatever. So how many possible ways? Is 6 possible ways? Well, if you know your combinatorics, it's a permutation problem. It's 3 factorial, which is 6. All right, so apparently there's 6 possible ways to do this. They did it one way over here, set up as one way. And so our task in this particular problem is to rewrite this triple integral by switching the orders. Now remember, when you switch orders, and we saw this with double integrals, you can't just switch the orders, especially if you know, one of them is constant and stuff. I think I recorded the. Yeah, if one of them's the outer limits always have to be constants. So let's keep that in mind when we're integrating. Let's integrate this in the different orders. Let's do, so this is dy dz dx. Let's do dx dy dz. Let's just go in order, run along and see how far we can get. What did I say? dx dy dz. All right, so let's take a look at that figure. We're going to say I want to integrate with respect to x first. I'm going to draw a line parallel to the x-axis from negative to positive. So the x-axis goes kind of like, if you're looking at it, it's going towards you. You kind of have to be coming from the back here. At some point, you're going to enter and then exit the region. Where do you think you enter the region from? X is equal to what? X is equal to 0. So you're going to enter through x is equal to 0, and then you're going to be inside of the region, and eventually you're going to come out of the region where x is equal to what? So it looks like it's coming out of this plane, and right now the plane says y equals 1 minus x. So you want to solve for x there, so you get it as an x function in terms of whatever is left. So 1 minus y. Okay, that's your y limits. So that's a 3D part. And after you do the one dimension in 3D, you're going to flatten it and you're going to look at the YZ plane. Because it comes in from the back of that solid and then it's going to come out of this plane. And you have to solve for X for that plane. All right? Yeah. No, I think that might be, is that the case? I think that might be right. So if you're entering through over here, then you'd be coming out of there, huh? Well, that sucks. Well, if that's the case, then we might have to look at this as a couple of different integrals. Yeah, I think we're going to have to cut this in different integrals. So what we need to do, just made our job a lot harder. What we need to do is we need to look at the YZ plane and look at how that YZ plane is broken up. I'm looking at the YZ plane here. It looks like it's going to be a box, right? But clearly, some parts of the YZ plane is going to give me a different value for other parts. And so what I want to do now is I want to figure out this line that kind of splits it. If we want to look at the shadow of that on the YZ plane. How are we going to find the shadow of that in the YZ plane? Oh, we have to eliminate X somehow between the two. Z is equal to 1 minus X squared, and Y is equal to 1 minus X. Or we saw that this is equal to, the same thing as X is equal to 1 minus Y. Right? So I think if we take this expression over here and put it in for X, then we're going to get something with a Y and a Z. Does that make sense? So let's put that in, and we get Z is equal to 1 minus Y quantity squared. Let's FOIL that out. 1 minus 2Y minus plus Y squared. So the ones will disappear, and then the rest of the signs will change. This would be 2Y positive minus Y squared. Okay, so we need to graph that, or we should know what the graph looks like. I think I have my YZ plane over here on the side. So if we graph that, I know that it's going to hit here. And what happens when I think it goes like this, like that, right? So the intercepts are 0 and 2. So I only care about it in that box, the 0, 1 box. So I think this is the curve that we want. And for this function, for this plane over here, this plane part, that's going to exist in the top part of this. Is that going to exist on the top part of this or the bottom part? So I think that's going to exist here in the bottom part, right? You guys with me? Feel like we should have done it differently first. Yeah. 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 So we're going to have to do two different sets of triple integrals if we want to do the dx, dy, dz. I think that's what we're getting at here. Anyways, this would be the region that we're looking at. And so if I wanted to integrate this with respect to y first and then z, I would need to draw a line parallel to the y-axis, right? Oh, that's not going to be easy either. Boy, what did we get ourselves into? Right? Because I need to take this parabola and solve for y. And it's being squared. Maybe this should have been the last thing we do. All right, let's try. Should I punch this out and see what happens, or should we try a different combination? What do you guys think? Different combo, and then maybe we'll come back to this. All right, let's take the same problem here. Just going to copy it on the next page. Let me actually look at it first and see which one would be easier. I think DZ first wouldn't be too bad. Let's try to do a DZ and then DX dy. Okay, so let's try that. DZ, draw a line parallel to the z-axis. You're going to enter the region at z is equal to what? 0. Agree? And then you're going to exit the region at z is equal to what? No, that's not a fire alarm. It's rant, rant, rant. All right, so that's our z. Now, after we take a look at that z and that's gone, we have x and y left. So we want to look at what happens on the xy plane. On the xy plane, you see this region over here, the triangle. So let's try to redraw that triangle here. So that's a triangle y is equal to negative x plus 1. Oh, it's the same thing as this. It's a plane. Or x is equal to 1 minus y. So if I were to draw a line parallel to the x-axis going into the region, I'm going to enter through x is equal to what? 0. And then I'll be inside of the region. I'll exit through x is equal to that line, 1 minus y, right? And then y limits are what? Constants, 0 to 1. Yeah. So after we do the first variable that makes it 3-dimension, then what you do is you look at the other two variables on the plane. So it becomes a 2-dimensional problem. Not necessarily. That weird example that we did yesterday was sideways. So it's clear that Z is probably not a good candidate for this as being first. So it really depends on the shape that you're looking at. So in this case, you could do it easily with respect to Y first and apparently with respect to Z first, but not so easily if you do it with respect to X first, because that's where we ran into a little bit of problems. But this one looks like it's pretty much done. And so all you have to do is write the integral. So triple integral. They didn't specify what the function was, so let's just say f of x, y, z. We're integrating with respect to z first, and our z limits go from 0 to 1 minus x squared. And then we integrate with respect to x next, from 0 to 1 minus y. And then we're going to integrate with respect to y from 0 to 1. So that's what I was expecting for our first problem. Okay, and almost just as easily, we can do dz dy dx. Where we would approach it the same way. The z is going to be the same, 0, 1 minus x squared. And now instead of the y, and instead of the x first, we're going to do the y first. So we do our line, we will draw our line parallel to the y-axis, and then we're going to enter through y is equal to 0. And then we're going to exit through this line again, y is equal to 1 minus x. I think the original problem had a dy first. And this is one of the ones that starts off with a dy, then we probably need to do the dy dx dz. But we'll do that after this one. So the x will be constants again, 0 to 1. And so we get a triple integral. It looks like it, yeah. dz goes from 0 to 1 minus x squared. dy goes from 0 to 1 minus x. And dx goes from 0 to 1. Okay. All right, so now let's do this one, dy dx dz. And I'll do it up here since it should be kind of similar to this one. So we draw a line parallel to our y-axis, and we're going to enter through the region and exit through the region on the same function. So we enter through the region with respect to y when y is equal to what? 0. We're going to be inside of the region and get out when y is equal to what? 1 minus x. And so now we look at its shadow on the xz plane, so that's what's left. And this is tricky because the x is going towards you. That's the positive x going towards you. And it looks like it has this shape, kind of like it looks like a semicircle, but it probably is more parabolic. And I think that equation is given here, because that's an equation that doesn't have a y in it. So it's a cylinder with respect to it going in the y direction. So I need x values for that. So I draw a line parallel to the x. I'm going to go in through that region at 0 again, right? But then I'm going to get out of that region through this parabola. Now I have to solve for x. So z is equal to, well, z minus 1 is equal to negative x. What? And then x squared is equal to 1 minus z. X is equal to positive negative square root of 1 minus. So it's either the positive part or the negative part. And what we could do is we could just try putting in a value like z is equal to 1 or something. Well, that's not going to help. How about z is equal to 0? That's not going to help. Well, x is positive when z is positive, so let's say it's the positive part. Right? So that's the tricky part that we were running into. And if you were to go back to that problem that we were doing, we needed to solve for y. You need to complete the square to be able to solve for y properly. And I'll do that, and I'll add it in our notes, and you guys can look at it later. But let's finish this off. What's the z limits? Constants, 0 to 1. Need a little bit more room. Maybe I'll write smaller. So dy, with respect to y limits go from 0 to 1 minus x. Dx, with respect to x, goes from 0 to the square root of 1 minus z. And then dz goes from 0 to 1. All right? So it's just a bunch of solving for equations and just a bunch of algebra. Granted, it's not algebra that we use all the time, but especially when you do the completing the square. We completed the square earlier this semester, but it's one of those things that is part of what your calculus arsenal should be. Questions? So I'm going to do this at a different time, and I'll just put the solutions here for this one. Looks like it's going to need to be broken up. So each of these will have two integrals. The dx, dy, dz, and then the dx, dz, dy will both need a couple of integrals to complete. Questions? So clearly there's some order of this that might be easier than another. So just be prepared for that. All right. Aside from volumes, we can use triple integrals to find the mass. The moments, now with three variables, the moment with respect to x is labeled as MYZ, and then it's given by those, and then you can find the center of mass that way. Hi. I think I won't expect you to be able to do something like this, but instead of saying do this in the 3 different ways or the 6 different ways, I'll just say do it with respect to x first, and then do it with respect to y, and then I won't have you do it with respect to z if it's as hard as the other one. But I think this level of difficulty with this page is not that bad, right? You're just figuring out the order of things, and where you have to split it up is something that I usually tend to stay away from, and I'm probably not going to give you anything like that on the test. All right. So again, these are just a bunch of formulas, and but this time it kind of gives a context or a meaning to what a triple integral might do for you. So instead of just saying, oh, a triple integral gives you the volume if your integrand is 1, well, your integrand isn't always going to be 1. And so what we need to do is we need to figure out what happens when your integrand is not equal to 1. And the meaning of that could be is that if your function of 3 variables gives you the density of a solid, then you can find the center of mass. Okay. So let's find a problem that does finding the center of mass. I'm not too interested, again, in the moments of inertia. So you can see that they have those functions, but we're not really going to talk much about that. Let's see if we could do a center of mass problem. Number 41. Ooh. Oh, it's a cube, so this will be easy. Let's do number 40. Oh, but it's a constant. It's okay. Oh, let's do number 42. Make up your mind. Tetrahedron bounded by the x equals 0, y is equal to 0, z is equal to 0. That's basically the coordinate planes. And then by another plane, x plus y plus z is equal to 1. So that looks like it gets cut off by that plane. And then your rho, your density function is just the function of y. And it's a function of x, y, z technically, but it's equal to y. So that means as it goes along the y-axis, the density changes, but if it goes along the x or z, it doesn't change. All right. So let's try. Let's try to draw the region. So with a plane, this thing crosses the x, the y, and the z all at 1. So it's this 4-sided tetrahedron or polyhedron that has 4 sides. And then we could decide now or later how we're going to integrate this with respect to x, y, or z first. I think we can integrate this with respect to x first, or z first. So if you integrate with respect to z first, you would draw a line parallel to the z-axis, and then you're going to enter the region through z is equal to what? Z is equal to 0. And then you're going to be inside of the region, and you're going to exit that region through the plane. And that plane is, you need it in terms of z. So that would be 1 minus x minus y. And then now you look at the two-dimensional graph that's left with the x and the y. And that looks like it's just the shadow that it's going to cast on the xy plane. It looks like it's going to be a triangle. Same sort of function, right? Y equals 1 minus x. Yeah. That should be z. Wow. Good catch. Okay. All right. So the y goes from 0 to 1 minus x, and the x goes from 0 to 1. So now we have the limits of integration for all the integrals that we're going to do, because you're going to integrate over the same region the whole time, over E, assuming this is E. And then your integrand is just y. So let's start off by finding the mass. The mass is equal to the triple integral. Well, the formula is up here. The mass is equal to the triple integral over the region of just the density function. Right? So let's set up our integral already. Triple integral, density function is just y. We're deciding to integrate with respect to z first, from 0 to 1 minus x minus y. And then with respect to y, from 0 to 1 minus x. And then with respect to x, from 0 to 1. Okay. This is a fairly easy integral, but for the sake of time, I'm just going to go to Wolfram alpha and have it compute it for us. So it's integral of the integral of the integral. I'm going to lose track of parentheses here. The inside for the first one is just y. And we're integrating with respect to z from 0 to 1 minus x minus y. Maybe parentheses for good measure. Close parentheses. And then we're going to integrate our x. No, we're going to integrate our y from 0 to 1 minus x. And then we're going to integrate our x from 0 to 1. I think we got all the parentheses figured out there. Okay, 1 over 24. All right, so now let's do myz, which is going to be almost the same integral. Except you have to multiply this with an x, right? X times the rho. So I'm just going to add an x in here, or multiply this by an x, and then run it again. One over 120. Yeah, pretty much. And then from here, you can already find x bar. X bar between the two of these, x bar is going to equal myz over little m. So that's 1 over 120 divided by 1 over 24. So whatever that is. And then you do the rest of them. mxz or zx, z times y, dz, dy, dx, etc., and then figure out the rest of them. Okay, so you guys can try this and maybe actually try integrating by hand. I will figure out the rest of these values using Wolfram alpha, and then that's it. All right, see you guys tomorrow.